Thank you, Madam Chair, dear colleagues from the scientific community. Well, my part is to give you an overview about the emissions and advanced treatment options for the emerging pollutants that are the topic of that conference here. And before I do that, I want to put a special focus on the effect that technologies that we apply for wastewater treatment actually were always a response to the environmental requirements. So there wasn't wastewater treatment just for doing wastewater treatment. There always were the demands coming from environmental protection or other pressures that led to the implementation or to the development afterwards implementation of certain treatment steps in wastewater treatment. And the first step definitely was the removal of acute toxicities in our surface waters and groundwaters, and the removal of some oxygen demanding substance, so that the oxygen demand occurring in the surface waters for the degradation of these readily degradable organic substances. So this was the first implementation of technologies that was worldwide done by usually activated sludge plants with a low sludge retention time. And after that problem more or less was somehow tackled, there was a new step. So we found out that it's not only the oxygen consumption in the rivers, but that there are some substances like the ammonia that directly lead to toxicity for fish, for example. So again, the reaction in the wastewater treatment technology was to find solutions for that, and that led to the implementation of the nitrification step in wastewater treatment plants. Just a very similar approach as the previous one, but just with an increased sludge retention time to allow slower growing bacteria to adapt to the wastewater and remove not only the ammonia but other substances too. And then after the nitrification step, we had an additional one, and here we already a bit heading towards this long-term effect, so not the acute toxicity test effects, but eutrophication, removing the pressures for eutrophication, NO3, or the phosphorus by precipitation, again, here by even higher sludge retention time. So this was the history of wastewater treatment. And right now we are facing a new challenge, a new approach that again requires the adaptation of the technologies we have available for the new challenges. So what we can say that today, the traditional, conventional wastewater treatment plants, according to the best available technology, they really were able to improve the environmental conditions in regards to carbon, nitrogen, and phosphorus compounds. But now we have these emerging parameters, and as we know and already heard, and we will hear it again during that conference, that even those plants that are operated and built according to the best available technology are not able to eliminate all trace pollutants down to a level where we may not observe some effects. So there's no effect concentration that we want to target finally. What we have to keep in mind when we speak about advanced treatment and improving technologies in wastewater treatment, we have to be aware that not all substances really are coming from the wastewater, and we really have to think about what are the pathways in the aquatic environment, and where can we really start to decrease the concentrations in the aquatic environment should it be necessary. For example, when we speak about the nulphenols, they are used in agriculture for formulation of pesticides. So even when we remove them completely with wastewater treatment plants, we will still find them in significant amounts in the surface waters because there are different or other pathways that contribute to the emissions. But we know that for some of the compound classes like endocrine disruptors, flame retardants, pharmaceuticals, wastewater definitely is the most significant input pathway. So when we observe a problem, we first have to do some material flow analysis to really identify where does the substance originate and what would be the best mitigation mechanism for that. So how can you do that? This is just a general working scheme for the assessment of emissions into surface waters that I borrowed from the EC. There is a new guidance document where there is really a very thorough approach and a guideline how things should be addressed. And you see that only these yellow boxes are the wastewater treatment plants, the urban and the industrial wastewater treatment plants, but there are a lot of other arrows that can direct substances into the surface water. And again, we have to know for the specific substances what error is the most significant one and where would measures, technologicals or other measures, be suitable in removing the substances. When we speak what's the contribution of the wastewater treatment plants on emission of substances, there was a very nice publication 2012 by the Joint Research Center in ISPRA that they coordinated a survey where they monitored the effluents of 90 wastewater treatment plants in a pan-European study, and again borrowed those two following graphs. And you see that some of the substances, and we already heard the presentation, the initial presentation, that for some of the substances really you find it in all wastewaters investigated. Of course, that does not tell you about the concentration. When we go to the next slide, the same substances now sorted according to the concentration where they were observed. We have an obvious picture, and this picture is not only a regional picture, but you really will find it everywhere in all wastewater treatment plant. So we have the benzotriazoles in a very high concentration. We saw that even from the surface water concentration in the River Rhine, the first presentation, and we have these artificial sweeteners like the saccharose and the acesulfam in very, very high concentrations. Again, artificial sweeteners are designed not to interact with the body. They are zero-calorie sweeteners, so that the body does not know how to deal with those substances. And the bacteria and the treatment plants do neither. So they just leave the wastewater treatment plant in the same concentration as in the inflow. And of course, in the surface waters, again, we have no biological removal of those substances, maybe a bit of photodegradation that would be suitable. Then we have the carbamazepine, and all other substances are in the low nanogram per liter range here. So what can we now do to remove? Should it be really necessary? And we say, well, we have to do something in technology, in wastewater treatment technology. We have to improve this, the removal efficiency. What can we do? Again, first I want to mention that the treatment plants we have nowadays, according to the best available technology, they do remove the micropollutants to a certain extent. Not to 100%, it's very much depending on the characteristic of the substance. But we have substances, as for example the estradiol, that's removed up to 90% with the modern plants. So it's more than nothing that happens nowadays, and we have to keep that in mind. The new technologies are not really new, they are only new in regard to the application wastewater treatment. So most of them are borrowed from drinking water treatment, so whether this is membrane technologies, activated carbon application, and chemical oxidation. But the problem is that in wastewater treatment we have to face a certain, issues that are not there in drinking water. In drinking water, we have a more or less stable matrix we have to treat. We have a more or less stable amount of water that we treat. In wastewater treatment, we have a lot of fluctuation I will speak about later on. This picture is intended to show you that with the modern treatment plants we have available with nitrification, denitrification, we can remove certain substances to a high extent. What you see here is we had the opportunity in Vienna when the wastewater treatment plant was rebuilt from a high-loaded carbon removal plant only towards a nitrification, denitrification plant. We were able to investigate at that time already some substances, micropollutants, and you see the black bars that even that high-loaded treatment plant was able to remove certain substances, usually that show a very high absorption potential to quite some extent. After the adaptation to the low-loaded nitrification, denitrification plant, you see that more substances are removed. And this is rather on the right side. And on the right side, you have an additional thing. Those are the endocrine disrupting chemicals. So we can remove these endocrine acting substances to quite some extent with the technology we already have implemented and available. But you see, again, even, for example, this CBZ, the carbamazepine, or the diclofenac, is not removed even by the low-loaded substances, and only when you apply additional technologies, as, for example, in that case, ozonation, you can increase the removal tremendously. So basically, we already remove, with the existing technology, certain compounds to quite some extent. I already mentioned when it comes to wastewater treatment, we have the wastewater matrix as one of the challenges for the design of advanced technologies, for the operation, and again for the costs. Basically, the wastewater matrix is a very complex, or wastewater is a very complex matrix. There's a lot of things there. We have dissolved and not dissolved particles. We have organic, inorganic substances. We have natural organic matter. We have the xenobiotics there. We have a substance in different orders in the concentration range, even in the inflow from milligrams down to several nanograms. So a broad span of of substances in quite different characteristical surroundings that we would have to remove in wastewater treatment. That wastewater matrix now really directly interferes or influences the treatment technology. So for example, the matrix can influence the filtration behavior when we speak about the MBR, the membrane technologies. There can be a competition in the elimination process for activated carbon when it comes to adsorption and binding sites. It can be in competition for the oxygen radicals when we speak about ozonation. And there can be some shielding of substances that are in, for example, the activated sludge floc, and therefore cannot be targeted by the ozone radicals. So basically, we can say when we want to apply advanced technologies, we have to reduce those matrix effects in order to really have a cost and reduction in the operational costs, in the overall costs, and that actually is something that is important for the acceptance of the technologies. So, in my opinion, the best available technology we have right now with the low-loaded sludge ages or nitrification, denitrification plants are something like a pre-requirement for the next steps. Otherwise, we're just wasting a lot of resources, a lot of ozone, a lot of activated carbon we need just to remove matrix that anyhow could be removed biologically by the low-loaded plants. Another issue that I want to focus your attention is the treatment targets. You are aware that when we design, when we plan, when we construct treatment plants, we're speaking about investments for 25 years, maybe even longer. So that means that we want, or we have to have the targets today that are really valid for the next 20, 25 years. And this is a problem nowadays. When we speak about substances, every paper you read, there is a new substance that emerges. And we are starting again from the beginning. Is that substance removed by that technology, yes or no? Then we know it, and after 3 months there is a new substance. We're starting again, so that brings us nowhere. So my favorite approach, or for a future approach, is the last red line, that we need to define biotests with different modes of action, and we say, well, our technology has to remove the content of the wastewater to that degree that there is no effect observed in this or that or a battery of biotests. Whatever substances are in there, what metabolites are in there, what is removed or not removed, the effect according to that test is not there. And that, I think, would be a good option to allow for the evaluation of technologies. And I think we here directly would have the link towards the integrity of ecosystems here. Actually, this, of course, is a new approach. I remember when I first approached the treatment plant operators in Austria that we want to do some biotests on cytotoxicity, neurotoxicity, genotoxicity, reproduction toxicity, and so on. They said, well, what happens when it comes out, it's that toxic, and that gets to the newspapers, then we have a big problem. And I said to them, well, calm down. The effluent of your treatment plant can't really be cytotoxic. You're working with biological systems, with bacteria that remove pollution. So those are, should the wastewater be cytotoxic, the municipal wastewater, then the biological treatment would not work. So stay calm, and we let us just look, and then we see what comes out, and the outcomes was really very promising. So from all the plants we investigated, we can't really say that there's a big toxicity problem of the effluents that we have even nowadays. But on the other hand, we can say, well, those tests are suitable for the technological evaluation, or the evaluation of technology, and we have the link to biosystems, but they are not really suitable for the operation control. So we have to prove that an activated carbon removal and ozonation is somehow suitable or really operated in a proper way, and those tests are not suitable, but again, very important for defining the technology available. That brings me to the technologies that are nowadays discussed. So one of them is the activated carbon. You know about the application of the activated carbon, high surface areas. Two aspects applied, as powdered form and as granular form. And there are different options that I will show you briefly how you can implement it. Generally, activated carbon is a very potential technique, but does not solve all problems. Neither does the ozone, nor is it really easy in the technological approaches. So there are some problems that we have to solve when we want to introduce the technology into full scale. We can lose activated carbon to the effluent, so we have a high loaded activated carbon, a powdered activated carbon particle that is highly loaded with micropollutants, and then we lose it to the environment, to our surface water, and then some macrozoobenthos organism feeds on that, and now it has really this highly loaded particle incorporated. So we have to prevent the loss of those very small particles. So those are technological challenges that are now investigated worldwide to overcome those problems. We have the problem with competition. Most of the studies that you see about the applicability of activated carbon is with new carbon, with fresh carbon. But what happens when one substance absorbs to the carbon, and then it's somehow replaced due to the competition of the adsorption by other substance, and then you lose it again in the effluent because the other substance has lower concentration but a higher affinity to the carbon. So you really have a competitive adsorption process, and that at a certain point can lead to the situation that you lose again what is already absorbed. So when you have a lab experiment, you remove the substance to 100%. But in reality, with all this competition in the matrix, it can lead to the point that at a certain point, again, you have a desorption of the substance. And so these breakthrough curves are very important to get an idea about the durability of those filters. Now just a few slides on how you could implement, for example, the activated carbon. So I borrowed the pictures from a working group I'm a member from the German Water Association, where we try to bring together the state of knowledge and provide that information to the operators. So basically, you can directly add the powdered activated carbon into the aeration tank. So with a dosage of about 30 milligrams per liter, 30 minutes of contact time, you mix it into the activated sludge, then you separate the sludge in the secondary clarifier. This is easily applicable. Of course, this addition of the activated carbon increases your sludge. Yeah, so you have more sludge. So what do you do with the sludge? When you incinerate it, that is commonly applied in Germany, for example, then it may not be the big problem. When you apply that in agriculture or for composting, then you have 20% of activated carbon in your sludge. Do you want that? So the final technology you really choose for your solution very much depends on the local situation, on the local infrastructure of the whole treatment chain and what to do with all the streams you're producing in the treatment plant. Another aspect is the post-treatment step with powder activated carbon. So you have your own contact basin with a sedimentation and afterwards a filtration step in order to prevent this powdered activated carbon from entering the environment. Or you can add you have an existing filter and you add the activated carbon, the powdered activated carbon directly in the right side to your filter systems. And another option that's more or less very similar to the drinking water treatment, you have a granular activated carbon filter at the end. Again, what you remove with activated carbon is really depending on the chemical structure of the substances. There are substances that are very, very polar that you cannot remove with activated carbon. Other substances you can really good eliminate. And you see from here just the middle two 10 milligrams powdered activated carbon addition, when you compare the bars, you find even very different removal efficiencies, even with the same amount of carbon. But in the one case, you just add it to the biological step and then you separate it again. And in the second part, you do some internal recirculation, so you can better benefit of the still available absorption sites of the carbon. So, and you get different removal effects. So this technical fineness, that is really the challenge for the implementation then. In regards to the ozone, is a very high oxidizing H, also with a high electron potential. It removes certain substances to a high content where you have a high electron density. But the big issue with ozonation is the formation of byproducts. And those byproducts, of course, or that formation has to be investigated. So how can you do that? Usually it's a post-treatment step. We usually nowadays apply between 0.5 and 1 milligram ozone per milligram DUC. So again, why do we not use the dosage in milligram ozone per liter, but in ozone per DUC? Because of the background matrix. So when you have a water with very high DUC content, you need more milligrams per ozone. Yeah? And that's, of course, the ozone, the production of ozone costs energy, and energy are costs, and cost is money, and someone has to pay for it. So you want to reduce the DUC before you really implement it. That's what we are trying right now. So that's our plant that we are building in that moment. So we have an ozonation tank, and afterwards, after the ozonation, we have 4 different options for treating or for post-treatment, ozonation post-treatment step. Because it makes them different, we want to investigate an post-granular activated carbon filtration, sand filtration, just at that volume, because it makes a big difference in the cost and operation, what additional treatment step you would have to implement. I spoke briefly about the tests that we need, and what could be one approach that you somehow link up the REACH, so the registration, evaluation, authorization, and restriction of chemicals in the EU. They have a certain test procedure for chemical safety. And what I was doing, that is considered wastewater that is released to the environment as a chemical substance released to the environment, and took the same tests, biotests as in REACH, to look on the effluents and the ozonated waters for testing. Yeah, what does it cost? This is a study from Adriano Jos from Switzerland. They did very detailed investigations. What you see that the conventional treatment is very much depending from the size of the treatment plant, so that's known. The larger the treatment plants, the lower the specific costs of the treatment, and the same applies for the 4th treatment step. So basically the numbers that are now reproduced by a lot of different investigations. So we can say for the larger treatment plants, whether this is ozone activated carbon, you see it's not really a big difference. Most probably it will come to a combination of both steps, but for large treatment plants it's about 30% increase in treatment costs. For the smaller plants it can be up more than an increase for 60% of the conventional treatment costs. That brings me to the summary. So basically, before we really start with implementing the technologies, we need to know where do the effects that we may observe in the environment do they come from. So is it really the wastewater treatment? Is it some other stream that is significant where we may have to start with reducing the pathways into the surface water? And it's not only the substances itself, it was already mentioned, chemistry is not a toximeter, so we need effects, we need agreed tests that we really can use, and standardized tests that we really can use for assessing the problems in the environment. We have to be aware that even when we apply advanced technologies for all wastewater treatment plants on that planet, we still will have the substances, of course, in reduced amount, but we'll still have them in the environment. So, because wastewater, again, is just one pathway of how the substances can enter. And we need the definition of treatment goals. We need environmental standards for substance and based on effects on an European level, in best case. Again, to evaluate the suitability of technologies, so whether the technology ozonation alone, activated carbon alone is suitable, or do we have to combine? I think that would be the direction that shows, because ozone has the discussion with the byproducts. Activated carbon does not remove the polar substances, but we can remove the polar substances quite efficiently with the ozonation. So when we have first an ozonation step and afterwards, for example, a granular activated carbon filter, then maybe that could be a really good approach. We need to define the treatment goals. Is it concentrations? Is it the non-effect on a specific test battery? And we need some tools for the operation control. This is still completely open. In regards to the summary, we have to be aware that the treatment plans we have now can remove some of the micropollutants to a certain extent. For example, the EU2, but a broad range of substances really are persistent to the processes that we have in the wastewater treatment plant. It's mainly adsorption, biodegradation, stripping, where stripping is not really relevant. But it's a potential aspect. Both the activated carbon and the ozone application are suitable technologies for removal of biologically stable or highly degradable persistent micropollutants. Both have their additional benefits. We have to mention that. So we have, and it's not really disinfection, but we have a significant decrease in the concentration of bacteria in the effluent of treatment plants. We have a decrease in the amount of antibiotic-resistant genes in the effluent. We have the removal of the humic substance, of the color, the brownish color of the wastewater. But again, both isolated considered are not able to remove all of the substances. And for that, I thank you for your attention.